Okay, so how is everyone today? Good, I hope. All right. So when we left last time, we were talking about polar plots and functions. So to sort of summarize, we had said that on the plane, so this could be the x axis and the y axis, like in the usual sense. And then for a particular point, we could say, well, let's consider that point right there. And what we're going to do is we're going to say, well, instead of naming that point xy, which is its name in the rectangular coordinate system, we're going to talk about in the polar coordinate system. And the way that you do that is you say, well, I'll measure the distance from the pole, which is the name for the origin. So from the pole there, I can measure that distance, and suppose it's the case that we measure that to be distance r for radius, and suppose also that we measure from the positive horizontal axis, we measure to the point in the counterclockwise direction, and we determine that angle is theta. Then what we're saying is that, well, in the xy coordinate system, the name of that point is xy, but in the polar coordinate system, the name of that point is r theta. Okay, and then these can all be, the xy and r theta can be related to each other in the following way. We can say that x is r multiplied by the cosine of theta. So the reason why that's the case is that if we were to set up this right triangle right here, then if this is the point xy like that, then what's the base of that triangle? Well, it'd be x, right? And then what's the height of this triangle? Y, right? So then, so ka toa, right? So cosine of that angle should be x over r, right? So x divided by r, and if I put the r on the other side, then it looks like that, right? X over r is cosine theta, adjacent over hypotenuse. So so if x is r cosine theta, what's y? R sine theta, for completely similar reasons. So this is how we can go back and forth between them. Notice that in the light of having done parametric equations, that kind of looks like a pair of parametric equations where the parameter is the angle, theta. So there's other formulas that relate xy points and r theta points. So that's a nice pair there. But notice if we square the first equation and square the second equation and then add them together, we get x squared plus y squared is r squared. Of course, in some sense, that's just the Pythagorean formula. If we take the y equation and divide it by the x equation, so this one divided by that one, then we could obtain that y divided by x is, well, assuming r is non-zero, the r's would cancel, and then we'd have sine over cosine, which is what? Tangent. And if you don't like the division of equations point of view, then you could just look at this triangle and just say, oh yeah, SOHCAHTOA, the tangent of theta is y over x. So what I just want you to see from these equations is that r theta stuff is on the right side, and xy stuff is on the left side. So you can go back and forth between these. So we left last time. We had talked about what a constant R function looks like. So if we were to plot just like R is say 5 for say pi over 6 less or equal theta less or equal pi, then what will that look like in polar coordinates? Right, it'll be a sector of, well, it'll just be an arc, right? Not the whole area. Sector meaning being interpreted as area. So this one, would look like this. It would be, here's the thing, and then, here's angle pi over 6, and then angle pi is the, the negative horizontal axis. So r equal to 5 would just be this arc of a circle of radius 5. So that's a constant function in polar coordinates. Similarly, if we say, for example, theta is I don't know, 5 pi over 6. And then we'll say for -2 less or equal r less than 3. So this is a constant function, but viewing the output as the angle and the input as the radius. So what will this look like when you plot it? It's a line segment, right? So it'll be a line segment. And it'll be at angle 5 pi over 6, which is, almost to pi, so like this. So that's angle 5 pi over 6. And then it says for radii between -2 and 3. So what do I need to draw? Well, where's radius 3, say? So here to here, so it'd be like right there maybe. So that might be r is 3. But then where would r equal where would r be -2? On the other side, right? So we'd have to go, so if that's 3, then maybe this is like -2. But I drew it closed. In fact, this needs to be open. So I'll say that that's 3, and then maybe over here is 2. So it would look like this. So that's curious. So what I want you to observe is that in the rectangular coordinates, where we're usually calling them x and y, a constant x is a vertical line. A constant y is a horizontal line. That's what constant things look like. But in polar coordinates, constant things look like either arcs of circles or these lines that go through the origin. That's what constants look like. Okay, so I asked you to consider the various polar plots that are in the book. So now we're going to consider a very specific one. So this particular one is called a cardioid. Not a remark. In fact, an example. I could say the following. I could say let r equal to 1 plus the sine of theta, and we'll do it for the full circle. For 0 less or equal theta less than 2 pi. All right. So such a thing is called a cardioid. So let's consider this for a moment. Ignore the 1 momentarily. So what is the biggest output that sine can produce? 1, right? It can't make anything bigger than a 1. What is the smallest thing that sine can produce? Negative 1, right? In magnitude, so like if you do absolute value, then 0, but sine is able to output a negative 1, right? So the biggest sine can be is 1. The smallest sine can be is negative 1, and then we're adding this 1 here. So what's the biggest that r can ever be? The biggest it can ever be? 2, right? So that's the biggest it can ever be. And what's the smallest that r can ever be? 0, right? Because, you know, the range of sine is negative 1 to 1, and then if you add 1 to that, the range of this is going to be 0 to 2. Okay? So, at what angle is, you tell me that the maximum output of sine is 1. At what angle is that achieved? At pi over 2, right? Straight up, a quarter turn. So that means that when we're straight up, that's the maximum value, and it's going to be at radius 2. Watching the angles. And so you tell me that the smallest output sine can achieve is negative 1. At what angle does that occur? 3 pi over 2, which is straight down. So at straight down, the radius should be 0. Right? Which means that when we get to angle 3 pi over 2, we'll be exactly on the pole. We won't have left. Fine. So with those considerations in mind, you know, we said that at straight up, so I'm just going to draw two tick marks here. We said when the angle is straight up, we have our maximum point of 2. When the angle is straight down, we have our minimum radius of 0, so there's going to be a point that goes through the pole. Okay, so now let's figure out, you know, what are going to be the angles, say here, and or what's going to be the radius here and here. So what's this angle for this one? That angle is 0. So what is the radius when the angle is 0? It's 1, right? Because sine of 0 is 1. Sorry, sine of 0 is 0, and then add 1 to that, you get 1. So we'd be here. And then what's this angle when you're on the horizontal but over there? So that's pi. So what is r evaluated at pi? 0. So again, we'll get this here. So those points are all on it. So, you know, you could go through and carefully plot a bunch of points. But after all, I said the name of this thing, the name of this thing is called a cardioid. Cardioid, like this. And if we were to plot lots and lots of points, you would observe that it looks like this. So you go up to that maximum, you go down to here, and then like this. Why is it called a cardioid? Looks like a heart, right? So then a terrible, awful thing that you definitely should do when February comes is you can tell someone, so this isn't, you know, that's not the way we usually draw a heart, that's the way, right? So to make the same cardioid, but to turn it around, you could say it like this. You could say I r equal to 1 minus the sine of theta u. All right. Don't say it unless you're brave, right? Okay. So it's called a cardioid. The subtraction is going to has the effect of making the minimum and maximum switch their angle position, so that has the effect of flipping it the way we usually draw a heart. Any question about that so far? So it's called a cardioid, and I could ask something like, well, at that point there, say, like right here. That's a point that's on the cardioid, right there. And then I could say, well, suppose I want the equation of the tangent line, right there. So that's going to be at angle pi over 3. I could ask, find the equation of the tangent line. So notably, I want the rectangular one. So what I want you to observe is that I gave you a situation where the coordinates are in r theta. They're in polar coordinates. But the question I'm asking you about, is in rectangular coordinates x, y. So do you see that I gave you the question in polar coordinates, but I'm asking you a question in rectangular coordinates? So in order to address this question, we need to first convert to rectangular. So how do we convert to rectangular? How do we get x's and y's? That one, right? We have to say that, okay, we have to have that x is r cosine theta, and y is r sine theta. Okay, well, so this is, that's nice, but then now we're going to substitute that in, right? So substitute in that r. So that would mean that the formula for x is, in fact, 1 plus sine times cosine. So distributing, that would be what? Cosine theta plus sine theta cosine theta. Okay, and what would the formula for y become? So I'm substituting this r, 1 plus sine, into there. Very good. So sine theta plus sine of theta squared. So now I know the rectangular position, the xy position of any point for a given angle, and the specific place that I was asking about was at angle pi over 3. So now to find the equation of any line whatsoever, you need two things. You need a point and a slope, right? So good. So to find the point, how are we going to do that? Right, just plug in. So plug in theta is pi over 3 there. So now here's the deal. Looking at the picture, please tell me what's your expectation about the SIGN of x and the SIGN of y. And the reason why I'm saying SIGN is because I don't want you to think I'm talking about SINE. So what's going to be the SIGN of x? Positive. How do you know that? Look where it is, right? What's going to be the SIGN of x? I mean the SIGN of the y coordinate. Also positive, because look where it is. And in a moment we're going to find the slope of that tangent line. What is your expectation about the slope? It's going to have to be negative. Why is it going to have to be negative? I mean, after all, right? It's going down. Okay. So we plug in that. So x evaluated at pi over 3 would be, some nightmare here. So this would be what? That's half. And then that's another half. And then sine of pi over 3 is square root 3 over 2, right? So that would be plus square root 3 over 4, because that's square root of 3 over 2 multiplied by 1 over 2. So that's the x coordinate. To find the y coordinate, again, just plug in pi over 3. So y evaluated at pi over 3. So that'd be square root of 3 over 2, and then plus square root of 3 over 2 squared, which is what? Plus 3 over 4. So do both of those have the correct SIGN? Yeah. All right. So that's how we find the point. So we can say, you know, therefore the point that we're looking for, x1, y1, is half plus square root 3 over 4 in the x coordinate, and square root of 3 over 2 plus 3/4 in the y coordinate. All right, how do we find the slope? Derivative of what? Okay, so the way that we'll do that is we're going to have to plug in. So notably, the input, okay, is, you know, this is not y as a function of x. So the input is not x. What is going to be the input? Theta, right? So we need to plug theta is pi over 3 into dy dx. But, you know, remember that most of the time that you've written dy dx, it was in the context that, that y was a function of x. But that's actually not the case. Rather, x is a function of theta, and y also is a function of theta. So how can we find dy dx? Right. So you've got to remember that dy dx, in fact, is going to be dy d theta, and then divide by dx d theta. All right. So let's do that quickly here. So fine. So what? dy d theta. So the derivative of that one. So that'd be what? Cosine theta. And then plus twice sine theta cosine theta. Now, pre-calculus is a prerequisite for this course. So when you see 2 sine theta cosine theta, something should be screaming out to you. It's sine twice theta, right? That's a trig identity that you should have memorized. Similarly, dx d theta, this would be negative sine theta, and then now I needed to do that. I'll do that with the I guess the product rule. So the derivative of the first one times the second, so that would be plus cos theta squared, because that's derivative of sine and then multiplied by cosine. And then now for the second one, it'll be keep that one as it is, so sine theta derivative of cosine theta. What's the derivative of cosine theta? Negative sine theta. So this will be subtract sine theta squared. And this also should be screaming at you something. This cos theta squared minus sine theta squared. What is that? That's cosine twice theta. It's not 1. Why is it not 1? Yeah, because it has to be plus to be 1, right? So what this is saying is that dy dx, the numerator is cos theta, and then plus sine twice theta, and the denominator is negative sine theta, and then plus cosine twice theta. Knowing formulas like that can really simplify your life. So then we could find the slope. So the slope is going to be of the tangent line is m is equal to dy dx, and then we're going to evaluate that at theta is pi over 3. All right, so at pi over 3, cosine of pi over 3 is what? Half? And then plus, so sine of twice theta. So what's sine of 2 pi over 3? These are things you must know. Must know. It's square root of 3 over 2. Okay, and then so sine of pi over 3. So what's sine of pi over 3? Square root of 3 over 2. And then the negative is in front of it, so I negate. And then plus. So what's cosine of 2 pi over 3? Negative half. All right. So then this will simplify a little bit. In fact, a lot of it. So then we could write this as a common denominator, and write this as the numerator as 1 plus the square root of 3, and then divide that by 2, like that. The numerator can be written like that. And then I could factor out a negative. And then write that as a common denominator, with a common denominator. So then it would read square root of 3 plus 1 and then over 2. And so, hey, what's that going to be? Negative 1, right? So as a result, we're saying that the slope is negative 1. So does that have the correct SIGN according to the picture? It does, right? So on such a question, especially if you're given a drawing and we say find the slope of the tangent at that point, and you respond with a positive number, that's wrong, but in some sense it's like categorically wrong. So like it couldn't even be right at all. That would be like saying that as a result of jumping out of the airplane, I fell up. This just doesn't make any sense. So then, in the interest of time, we'll just move on. But now, do you remember that the point slope formula for a line is this? So at this position, you just plug all that stuff in and then say, here it is. Any question about this example? That's okay. All right. So now we're going to move to other stuff. So is there anything else that's curious here? No. So then, just briefly mention, just looking at the picture, are there going to be, in this picture, are there going to be any vertical tangents? Yeah. How many? There's going to be 2, right? 1 and 2. And you should expect, more or less, one of them should be an angle that's on the right half plane, and the other one should be an angle on the left half plane. Are there going to be any horizontal tangents? Yeah. How many? More than 2. 3, right? So there's going to be one at the top, and then, in fact, 2 on the bottom, right? One there.
Yeah, even though it's the same line.
Well, yes, there's going to be 3 solutions because it's going to occur at 3 different angles. So it's going to, angularly, like this, blah, horizontal tangent, and then blah, horizontal tangent, and then one more horizontal tangent where the angle is concerned. So there'd be 3 different angles where it occurs. And then I drew that big point there, so you can't really see it, but that's pointy, sharp. It's a cusp. So that particular place would not be a horizontal tangent. But you need to be careful. You need to be careful concerning that point, because one of those points, one of the x's, or either the x or the y, meaning this x or that y, its derivative with respect to theta is going to be 0. But that's not enough. It's not enough for that to be the case. Okay, so then I'll mention one more thing, and it's say this. Suppose we take that cardioid, which was 1 plus sine theta, and suppose I change it to this. I say r is 1 plus, say, I don't know, twice sine theta. So now the story is different because, you know, I asked, what's the max of sine, what's the min of sine, blah, blah. So in this case, what is the maximum value of 2 sine? 2. So the maximum value of this altogether is 3. And what's the minimum value of twice sine? -2. So what's the minimum value of all this? -1. So that means in some cases, the radius is going to become negative, right? Meaning that the angle is pointing one way, but the actual plot is in the negative direction. So if we do this, it'll end up looking like this. So, you know, according to the things we just said, you know, there's going to be a maximum at 3, and it's going to occur at the angle which is straight up. There's going to be a, you know, at 0 and pi, sine is 0, so it'll just be 1 here and here. And then what angle produces the minimum value? Three pi over 2, right? So 3 pi over 2 is this angle right here. So interpreting that, you know, as theta is 3 pi over 2. So plugging in 3 pi over 2, sine of 3 pi over 2 is -1, multiplied by 2 is -2, add 1 is -1. So when the angle is 3 pi over 2, the radius is -1. So where do I need to plot the point? So, right. So here would be 1. So where's -1? Up there, right? Right. So angle 3 pi over 2, but -1 in that direction. So now looking at this, this is you know, going to end up being cute, and it looks like this. So you start here, and you proceed up to the maximum, and then you proceed over to that point. Okay, so now here's this angle right here. So you know, there's an angle that's, you know, like right here, like that, say, and that might be something like if this is 3 pi over 2, then this would be 9 pi over 6. So this could be 8 pi over 6, 4 pi over 3. Okay, so before we get here, we're still positive. So that means that there's going to be some point that's like, you know, like right here. So we're gonna go through that point. But as this angle, if you can imagine that I could grab this this thing and wiggle it around, you'd watch us tracing that little bit of red right there. So wiggle that angle, and that point's wiggling. So when you take this angle and move it to 3 pi over 2, what's going to end up happening is it's going to quickly sweep through here and then go like that. And then it'll sweep back through the origin and do this. So this is like a, you know, like a cardioid, but it's got this loop in it now. Interesting. So this entire inner loop, that inner loop is all the points where the radius is negative. Interesting. Okay. So you can imagine if you take this 2 and you squeeze on it and squeeze it down to 1.5, so it would read 1 plus 1.5 sine theta. That would make the loop smaller, so it would go like squish the loop smaller. And as you make the 2, you squeeze the 2 and get it closer and closer to 1. When it finally becomes 1, it becomes pointy like that one. But if you make the 2 bigger, then this loop can be even bigger. Interesting. So generally the form of these is the following: is that R can be A plus B multiplied by the sine of theta. And your ungraded homework, but something you should study at home, is that what needs to be true about A and B? What needs to be true about A and B? What will make concerning A and B? What will make big loops? What will make little loops? What will make them? What will make this loop be not a loop, but actually a pointy thing?
Greater than 0.
So I
Zero make
leave it to you, okay, to consider it. So consider all possible combinations. So consider combinations of A and B. Okay. So now that we've talked about calculus from the differential point of view, so for example, we said, here's a thing, find the equation of the tangent line. So that's calculus from the differential point of view. Let's look at calculus from the integral point of view, which is to say, let's find some areas. So, last time we talked about. So this is now section 10.4, I think. So last time we said that in the xy plane, so if you take an x interval, an interval of x's, say like these x's, from A to B, so that interval of x's, and you take another interval of y's, say like this y to that y, C and D. Then you could draw what does the Cartesian product of these two intervals look like? Well, it looks like a rectangle, right? So, which is to say that what is the set AB like that cross CD look like? That means the set of all points where the x coordinate comes from there and the y coordinate comes from there. Well, the picture looks like this. A rectangle, right? Which is why this is called the rectangular coordinate system. Okay, so what I want you to interpret this is that x's come from that set, and y's come from that set. So, what if instead of that, we say, okay, let's consider thetas, which come from, for sake of argument, say like pi over 6 to pi over 3 open. So thetas come from there, and then cross, say, 1 to 3 radii. So in rectangular coordinates, that's what that set looks like. It looks like a rectangle. What is this set going to look like when viewed in polar coordinates? Well, let's consider. So we need to draw that angle and that angle, right? So pi over 6 is something like this. And then what's pi over 3? Something like this. So that's pi over 3. And now, what does radius 1 look like? Not a line. What does a constant radius look like in polar coordinates?
Arc.
An arc of a circle, right? So then we draw an arc. We draw, this part of a circle of radius 1. And then what does radius 3 look like? Right, a bigger arc, okay. So then, you know, something like this. So this would be r is 1, and this is r is 3. So can you see, this is what we're talking about. We're talking about that thing. Okay, so it's like, you know, it's kind of like a rectangle, except it's, you know, smeared out. And if we were to go all the way around, say the angle from angle 0 all the way to 2 pi, then that would be a ring, a washer, you know. It would look like a washer. The name for that thing when you go all the way around is called an annulus. That's its name. So that's a disk with a disk in the middle deleted. And because something between two angles is called a sector, this shape is called an annular sector. Okay, so the area of a rectangle is super straightforward, right? It's just base times height. Easy enough. So what we want to be able to do is we want to find the area for an angular sector, because here's the deal. Remember in calculus when we took the plot of a graph of a function, and then we said, hey, let's cut that the area that's between the function and the horizontal axis into little rectangles. And then when the rectangles are above, we're going to say that those are positive, and when the rectangles are below, those are negative. And then we're going to cut that area into infinitely many infinitesimal rectangles. You remember that? That was a good time. Now we're going to cut areas into infinitely many infinitesimal angular sectors. You know, because that sounds like a good thing to do, right? So instead of cutting stuff up into rectangles, these things, we're going to cut them up into those things. But the trick only works if every time you have one of these simple shapes, you can find its area. So base times height, that's as easy as it gets. We need to be able to say what the area of any given angular sector is, annular sector. Okay. So the area of an annular sector, All right, so then I'll say the following. Suppose that here's the pole, and we've got two angles. And since we want this to be generic, I'll say that this is angle theta 1, and this one angle theta 2. Good. And, you know, we need two radii, so I'll say that this is a radius, and this is another radius. So to be generic, I'll refer to this as radius 1 and radius 2. So now we need a couple ideas. So the first idea is that you know, what if we had just the whole an entire circle like this, right? Which is to say that we just had like R2 is you know, we just have this one radius. So the big one is that, and then the small radius is 0. So this is like a trivial annulus, where an annulus is a disk, and then you delete the disk in the middle. But the disk in the middle is you know, not there. So this is a circle. So what's the area of this thing? Okay, pi r squared. So its area is pi r squared. That's straightforward enough. But what if instead of that, we took a circle of radius r, and then, you know, we took our pie slicer, or, you know, the pizza thing, you know, that thing, and then we cut it there and there, say, at angle theta 1 and angle theta 2. Okay, so which is to say that we just have this much. So what's the area of just that much? So what's the area of the whole thing? Pi r squared, right? And then the question is what if we just take that much angle? Okay. Well, if I make my life simpler for a moment, and I just say that I'm going to name this this angular difference, delta theta, meaning theta 2 minus theta 1. Then that, the angle from there to there is delta theta. And then what's the full angular measure of a circle? 2 pi, right? And then if we're only taking that much, we're taking some fraction. The fraction of the circle that we're taking is delta theta over 2 pi, right? So the area of this would be the full area of the circle, pi r squared. And then now we have to multiply by the fraction we're taking. So what's the fraction we're taking? Delta theta over 2 pi. Okay, so do you observe that the pi's cancel? Okay, so we could write that this, in fact, is half r squared delta theta. So that's the area of that. And then what if we had this? We wanted to find the area of an annulus. So if this if the small radius is r1 and the big radius is r2, just like in the picture, and we want the area of the annulus, then can you see that the formula for this is just the difference of the areas of the two circles? It's the big one minus the little one. So this would be the big one, so pi r squared, r1 squared minus pi r2 squared. Yeah? Okay, so then I could simplify this formula a little bit. I could factor out a pi, right? And furthermore, this is one thing squared minus another thing squared, so that's the difference of squares. Now the difference of squares factors in a nice way. How does it factor? So what does the difference of squares factor as? So like a squared minus b squared factors as what? That one, a plus b multiplied by a minus b. So the binomials a plus b and a minus b, those are called conjugates, right? So the difference of squares factors as the product of conjugates. That's the phrase there. So then you could say that the area is pi multiplied by what? I'll say the sum, r1 plus r2, multiplied by the difference, r1 minus r2. Now we're going to be interested in the difference. So just like the difference of the angles we measured, we named delta theta, what are we going to name that one? Delta r. So we could say that this is equal to pi times r1 plus r2 and then delta r like this. And then for reasons that aren't entirely clear yet, so when you add two things up, that's neat, but when you add them up and divide by 2, what is that? That's the average. So I want to make this average radius. So I'm going to put this over 2, so blah, blah, and then over 2. But the cost of doing that is I have to put a 2 somewhere else, right? Right. So I'm going to say that this is twice pi. So there's the multiply by 2, and then multiplied by this one, so r1 plus r2 over 2, and then delta r like that. So the formula for the area of an annulus is twice pi times the average radius times the change in the radius. All right. And finally, combining all these things, suppose that we just want a fraction. Instead of the full annulus. What if you can imagine I drew the rest of the annulus going all the way around. What if we just wanted that fraction? So we're naming this delta r. We're naming this delta theta. So we want to take the area of the full annulus and then multiply it by the fraction that we actually traversed, right? So the area should be twice pi, the average radius, times the change in the radius. So that's the area of the full annulus. And now we need to multiply by the fraction that we actually took, which is what? Delta theta over 2 pi. And do you observe that the 2 pi's cancel? Oh, terrific. So this will be what? It'll be the average radius multiplied by the change in the radius multiplied by the change in the angle. Ah, good. Now we have a formula. Now I have a formula for this. Any question about this? Okay. So, oh, we're out of time. Okay. So, well, I want to write down one thing, and then we'll be done. So I just want to write down the formula so you can see it and think about it. Yeah, we have to. Well, it can wait. We'll do it. We'll do it next time. So y'all have a nice whatever day it is. Wednesday.